Hi everyone. In this video, I'm going to introduce what's called LISREL notation, which is going to be specifying the parameters that we're going to be estimating as well as for one variable in a path analysis model. Now we're going to be working with the aspiration achievement model shown here. I've replaced the names with x's and y's. X's are exogenous variables, y's are endogenous. And it'll become apparent why I've done that in just a moment. LISREL, L-I-S-R-E-L, was created by Yorskog in the 1970s. It was a software package, and it stands for Linear, Structural, Relationships. It was a software written to estimate parameters in a structural equation modeling, a very impressive software back in the 1970s. And the way that Yorskog wrote it was by defining parameters, and then in the syntax code you would tell LISREL, the software, which parameters to estimate and which, say, to fix to 0, or maybe place constraints on. But it needed a way of identifying parameters specifically. Now I'll show you the LISREL notation. LISREL is still a model that's used, a software that's used to this day, but even if you're not using LISREL, for example, using M+, knowing the LISREL notation can be very valuable, especially when you're writing a paper and you need to report your parameter estimates or the model you're using say, matrices. The first parameter I'm going to introduce is called gamma. Gamma is a regression coefficient. When we are predicting an endogenous variable using an exogenous, so we're using an exogenous variable x to predict an endogenous variable y. As an example, x1 is predicting y1, so we're going to call that gamma. x2 is predicting y1 as well, so that would be gamma. Then you have x1 predicting y2, that's another gamma, and x2 predicting y2 is another gamma. We are not going to use it to refer to y1 predicting y2. We'll use a different symbol for that regression coefficient, even though it has the same meaning as the gammas. It's just a regression coefficient. Now, because we have 4 gammas, we have to make them distinct, essentially. The way we do that is we put subscripts, and we're going to put 2 numbers in the subscripts to refer to the gamma we're referring to. And the first number is going to refer to the endogenous variable being predicted, in this case y1, and so it's going to be a 1. The second number in the subscript will refer to the exogenous variable doing the predicting, which is x1, so we'll call that gamma 1, 1. And now this gamma here for x2 predicting y1 will be gamma sub 1. And now we're going to put a 2 in there, indicates the second endogenous variable doing the predicting. And then when we're predicting y2 using x1, it will be 2, 1, because the second endogenous variable using the first exogenous. And then here it will be gamma 2, 2. Well, we can take these gammas and place them into a matrix. It's called the gamma matrix. Now, this matrix has the dimensions of m by n, where m is the number of endogenous variables. So rows are defined by endogenous variables. N is the number of exogenous variables, or the x's. So in this case, if we just take these 4 parameters based on their subscripts, the first number refers to the row, the second number refers to the column. So this gamma 1, 1 goes here, first row, second column. Gamma 1, 2 goes here, the first row, second column. Gamma 2, 1 comes here, second row, first column, and then finally gamma 2, 2, second row, second column. That's how we store our parameters. Now, another way to think about it is that the rows are defined by y. So we have y1, y2. That's what's being predicted. And then finally, the columns are defined by x's, x1, x2. Now, the fact that this is a 2 by 2 matrix is just because we have 2 exogenous and 2 endogenous variables. If we had 3 endogenous variables, for instance, it'd be a 3 by 2. And not all these parameters have to be estimated. For instance, if I fixed gamma 2, 2 to 0, this would drop out and it would just become 0 in this matrix. Now, as I said earlier, you'll notice we did not put a regression coefficient for y1 predicting y2. That will be the next parameter. We're going to call that beta. So beta is a regression coefficient, but in this case, it's an endogenous variable predicting another endogenous variable. And so here, that only happens once. We have y1 predicting y2. And using the same convention with respect to the subscripts, we're going to put a 2 here because we're predicting the second endogenous variable, and a 1 here because we're using the first endogenous variable. We can store these beta parameters into a matrix, where the matrix is an M by M. It's a square matrix. The diagonals in this matrix are 0. Because right here, if you think about row 1 is y1, row 2 is y2, and then up here is y1, y2, referring to y1 is being predicted by y1. We're not doing that. So that's always 0. Predicting y2 with y2 is always 0. So the diagonal of this square matrix is always 0. We have beta 2, 1 indicating we're predicting the second endogenous variable using the first. And up here at 0, we're not predicting the first endogenous variable using the second. So even though it's a square matrix, it is not a symmetric matrix. And by the way, if we did not have this path in here, predicting y2 and y1, this would be all zeros. The next parameter refers to the variance and covariance of our exogenous variables, our x's. And we're going to use the parameter phi. And so we're going to have a phi here. This is going to refer to the variance of x1. A phi here will be the variance of x2. And then, often, we're going to have a covariance between x1 and x2. So phi in this case is the variance, covariance among the exogenous variables. Okay. We can store that in a phi matrix that's going to be square and symmetric. That is an n by n, number of endogenous variables. The diagonal are going to be the variances of our exogenous variables. So you can see here we're going to put a phi here, and that's going to refer to x1. And so the subscript is going to be 1, 1, 2, 2 here, because they're the variances of the same, of the variable, which is a covariance with itself. And then the covariance between x1 and y2, you can either write 1, 2 or 2, 1. It doesn't matter. So here we'll have phi 1, 1. That's the variance of x1. Phi 2 is the variance of x2. And then finally, phi 2, 1. And I'm going to leave the upper part here blank because it's a symmetric matrix, and phi 1, 2 is identical to phi 2, 1. The next parameter is not something we actually estimate, but it represents something important in our model, and that essentially is the error, or unexplained part of the endogenous variable. And the symbol we're going to use is zeta, the Greek letter zeta. So this is going to be the error in the endogenous variable. In the endogenous variable. And so we're going to have a zeta 1 and a zeta 2. The 1 because we're at y1, 2 because it's a second endogenous variable. Now this, even though we're not estimating zeta 1 and zeta 2, they represent something, we're still going to put it in a matrix. We're going to be in a zeta matrix. And the matrix is going to be an m by 1, where we're going to have zeta 1 and zeta 2. We're going to use that in the next video when we start writing out equations for our path model. Now the final parameter we're going to estimate is the variance of our errors, the variance of these zetas. Now in this case we're going to have a variance of the error for 1, so we're going to have a psi here. We're also going to have, this is going to be the psi symbol, that's going to represent the variance of y2, for instance. So we use this symbol psi. That again is the variance, but also covariance among the error, or zetas, if if you will. Okay. Now, I say covariance because we could actually correlate these errors if we wanted. You have a double-headed arrow in here. We don't. In this case, we fix it to 0, but it is possible. So we're going to store these variances into a matrix that's going to be an M by M, number of endogenous variables. It is a covariance matrix, so it's symmetric and square. The diagonal will be the variance, so this will be psi 1, 1. So that would be the variance of the unexplained part of y1. Then we're going to have psi 2, 2. That's the variance of the unexplained part of y2 or zeta 2. And then if we did have a correlation here, we'd have psi 2, 1, but we don't, so we're going to fix that to 0. Because it's symmetric, we don't have to specify the upper part here. Well, those are all the 5 parameters in a path model. When we get to latent variables, we'll introduce 3 more parameters. And these were very valuable when using LISREL because this is how you told LISREL which parameters to estimate and which ones to fix to 0 or possibly constrain. But even if you're using another software package such as M+, although you don't need to know these parameters to write the code for M+, it's still valuable when you want to write your papers to summarize where the parameters go. And in the next video, I'll show how we're going to use these matrices to write the path model as an equation.